everyone. Welcome to today's Quantopian webinar, Reinforcement Learning in the Presence of Non-Stationary Variables. Today's speaker is Simon Ouellette. Simon is a machine learning specialist and a quantitative trader at a proprietary trading firm. Starting his career as a software engineer about 15 years ago, he increasingly gravitated towards data science roles. His passion for finance was acquired 9 years ago when he worked in New York City for Bloomberg. Since then, he has been applying data science to trading, first in an amateur setting and eventually in the current professional environment. Thank you, Simon.
Okay, so I'm going to be talking about reinforcement learning in the context of finance with a specific emphasis on the problem of non-stationary effects. So I'll start with a simple question. Does it work in finance? Does reinforcement learning actually work in finance? And if you ask most data scientists and most quants in the financial industry if machine learning works well for trading, they often don't answer very favorably. And most people who have tried to use it in finance have an unconvincing experience with it. And while most industries are currently being vastly transformed by AI and machine learning, the fact is that the world of trading is lagging behind. Most systematic trading algorithms in use are still surprisingly basic. And looking specifically at reinforcement learning, I was only able to find two very specific use cases in the finance literature where it has been used successfully. That first case is optimal trade execution, where the problem is really just a matter of either purchasing or liquidating a large quantity of assets in a way that will have the least market impact so that we get the best prices. And the other one is option pricing, because option pricing is based on the Black-Scholes conceptual framework, which has several assumptions, one of which is the assumption of a continuous hedging with no friction and all that. But the way that reinforcement learning can be used to improve the option pricing is to simulate the optimal but discrete hedging that includes things like transaction costs. So by including this reinforcement learning agent in the process of option pricing, it supposedly gives better option prices. But more directly, as an alpha discovery mechanism or as a trading strategy, not much success is heard about. And I would argue that the main reason is what I refer to as the curse of non-stationarity. So this is an example of a non-stationary stochastic process. So we have several different trajectories that are allowable by the process, or here it's actually several examples of trajectories of this process. And in particular, this is a random walk. So this is a specific kind of non-stationary process, and the trend is 0, and the scaling parameter is 0.5, and the random variable is a uniform distribution, although typically it's more a normal distribution. But in this case, it's a uniform. So you can think of this process as the relationship between two variables that you're trying to estimate. It could be the correlation between two stocks, and this correlation changes over time. It could be the relationship between some factor and the price movement of an asset, and that changes over time. But throughout this presentation, the example we will work with is a pairs trading example. So the non-stationary variable will represent the true underlying spread. When the pair diverges from this spread, we expect it to mean revert to it. And that would be easy if this level of mean reversion were constant over time, but it never really is in practice. It is something that tends to drift. So our goal will be to learn a strategy that will trade optimally on this pair. And typically, the way traders work is they use some historical data and they optimize their strategy on it, or they research a strategy on it. And let's say that this is the historical trajectory that we are now looking at. And when you think about it, this is really just one specific realization of the underlying data generation process that we looked at in the previous slide. Now, imagine what happens if we optimize an agent on this. It would assume that the way to optimally trade this particular historical realization is to take a long position. And so this means that our learning agent, our reinforcement learning agent, when trained on this particular historical realization, it will probably simply learn to take a long position on the spread. Or if it's sufficiently complex, it might learn some kind of mean reversion in the middle or something like that, but it would learn something that is very specific to this particular realization. And then in the next few data points, you might get something like this or something like this. And now suddenly the behavior of taking a long position is no longer optimal. And yet this is the same data generating process that we're talking about. So in other words, we have overfitted, and it didn't take a very complex model to do so. Even the most simple statistical model would have learned a trend that isn't really there. So this overfitting occurred because this latent relationship that we're trying to learn is non-stationary. Its probability distribution evolves over time. So to be more specific, so what does it mean for time series to be non-stationary? It means that the time steps of these time series are not independent from each other. The probability distribution at time t depends on the value of the random realizations cumulatively at time steps t-1 to some t-n. So as a result, the entire time series is only one outcome of a random experiment. So in other words, this is really a one sample data set. And the average of all time steps isn't a sample average, it's a time average of that one sample. Now, if you contrast that to stationary time series, now in stationary time series, the time steps are independently distributed, and I would add identically distributed, and the distribution at time t is the same as time t-1, which is the same as time t-2, and so forth. So the parameters of the underlying distribution are constant. And when that happens, now you can apply the law of large numbers and you can do normal statistics and machine learning on that data. And this is because in that case, the independence of the different data points means that each data point is an independent outcome of the random experiment. So then you have an n sample data set rather than a one sample data set. So I'm going to show this with some code. So demo part 1 and demo part 2, which will be made available to you. So let's start by describing the data generating function for this demo, which is this one here, stationary dgp.py. So we have two co-integrated time series, x and y, and y is expressed as x plus the spread. Now epsilon represents the spread between the two, and x itself is just a random walk. So this epsilon is modeled as an Ornstein-Uhlenbeck process, which is simply a mean reverting process. So the long-term mean to which this spread reverts is the value that will be in mu. And theta represents the speed at which the process tends to revert to that mean. And then we have the stochastic part, which represents the random shocks that cause the spread to diverge from this mean. So let's visualize an example of that generated data. So this is what it looks like. You have the mean at 100 that is constant, and you have a signal or a price process that revolves around that mean. Okay. So while this is running, because it takes a bit of time, I'm going to explain the reinforcement learning agent itself. So in this function, the replay function, we have an XGBoost model which learns the state action value function. Now I should quickly explain two things. First, what is XGBoost? And second, what is a state action value function? So XGBoost is an open source gradient boosting library. The gradient boosting is a machine learning technique where we combine multiple weak models into a single strong model to make predictions. It does that by first learning one weak model and then by training the next weak model on the residual errors of the first one, and so forth, for however many models we choose to combine into one. And in the case of XGBoost, as is often the case in gradient boosting, these models are decision trees. Okay, so that's for XGBoost. Now, the state action value function relates to reinforcement learning. So it refers to a function that takes as input the current state of the agent's environment and some action that it took in that specific state. and it outputs the expected reward for taking that specific action in that specific state. And the reason we care about such a function, the reason why we're modeling it, is that it will tell us, given any state of the environment, which is the action for which we expect the highest reward, and we will usually take that optimal action. Although we will see that there are cases where we want to explore different behaviors. So the way we train the XGBoost model to learn this state action value function here is by going through each state in the agent's memory of its interactions with the environment. And for each state, there's an action associated with it. And then there's a reward that was received as a consequence of taking that action in that state. So the state and action become our input features to our model, and the reward becomes the label in our training data set. And then we proceed to training that model. So this way we learn the state action value function. And now let's look at the function where the agent actually acts in its environment. So at every new time step in the environment simulation, this function will be called. So we receive a state. And then the first thing that we do is we evaluate whether it's time to explore a new behavior or to behave in the way we think is optimal. So this is the well-known exploration-exploitation trade-off in reinforcement learning. So if we explore all the time, we're able to better learn the relationship between various actions and various states and their corresponding rewards, because we visit a wide range of state action combinations. But because our behavior is random, our performance isn't great. But at the opposite end of the spectrum, if all we do is act based on our belief of what is the optimal behavior, then we never get a chance to learn better state action combinations. So there are a wide variety of different strategies in the literature with respect to balancing these two things. But for the purpose of this demo, I am choosing a simple decaying epsilon greedy strategy, which means that epsilon% of the time we choose to explore, and the rest of the time we choose the optimal action. And this epsilon value starts at 1, so I can show you where that variable is. This is the epsilon variable. It's initialized at 1, and it decays gradually throughout the training process. And in fact, when I evaluate the agents rather than training them, I set this epsilon to 0 so that it behaves optimally 100% of the time. Okay, so when it does behave optimally, here, what it does is that given the current state, it tries out the 3 possible actions. So the possible actions for this specific agent is to go long, short, or flat on the spread. And then it chooses the one that has the highest expected reward based on our XGBoost approximation of the state action value function. This is where it chooses the maximum reward action. Okay, so that sums up the reinforcement learning agent. Now let's finally look at the actual simulation loop in our first demo. Okay, so we go through every single time step in the generated data. We construct the state vector as the current spread, so y minus t at current time t, and the current position. So this contains -1 if we're currently short on the spread, 0 if we're currently flat on the spread, and 1 if we're currently long on the spread. So we feed this information to the agent, who then chooses an action to take. So if we're currently training the agent, rather than just evaluating it, we calculate the reward that corresponds to taking the current action in the current state. And we save the state action and reward combination in some memory, essentially. Now, outside of that loop, we train the agent 100 times on the same data, which is the data generated here. So this represents the historical data that we train on. So we generate some time series that is fully stationary. And here we simulate the process of using some historical data, training an agent on that historical data, and then evaluating that same agent on new unseen data. So in that evaluation loop, for every single iteration, we actually generate a new time series that was never seen by the agent. So we're showing by this demo that if the underlying data is fully stationary, then yes, the agent will learn an optimal strategy, and this optimal strategy will generalize to the validation set, the validation data. So what we see on these charts on the left, this is the learning curve. So during the iteration loops, the loop iterations for the training loop, we see that its performance gets better and better. And then we have this testing loop. We see that the performance is somewhat similar to the best performance during training. So it learns something and it generalizes well as expected. So we can see here the training PNL is 34.9 and the out of sample or validation PNL on unseen data is 32.4, so pretty close to the training PNL. Now, in demo 2, we use the same training and testing code. The only thing that differs from demo 1 is that the DGP, or the data generating process, will contain a non-stationary effect. So we use this one here, time varying DGP. So the underlying true spread, the value mu, to which the spread tends to revert, it will be allowed to drift and jump over time. So it is no longer something that is stationary, it is something that is non-stationary and drifts over time. So we see that this is what the data looks like. And we run this. Now, while this is running, I need to mention another thing that is different in this code, and it is the fact that I have a rolling estimate of the true underlying spread. So let me show demo 2. So here, I have some slightly different code when I generate the state vector. So I calculate the mean of the last n spreads in an attempt to estimate what is the latest level of the spread. And then I subtract this value from the current spread to give a sense of how much the current spread has diverged from the current level of the underlying mean of reversion. And I added this because often this method of rolling estimates is claimed to be the answer to the non-stationary problem, even in such great books as Sutton and Bartow's classic reinforcement learning book. And it is true that it helps. It does let the agent adjust to slowly moving effects if we recalibrate at the right frequency. But here I will show that it isn't such a rigorous solution to the problem. It's more of an approximate technique, and we will still end up overfitting. And the fact is that no matter at what time window you look at a non-stationary variable, it is still non-stationary. It's just that within that time window, it has less time to diverge. Therefore, the estimation error is reduced. But ultimately, it's always just an approximate approach, and it works best for slow-moving non-stationary effects. Now, that being said, I still recommend using this sort of dynamic recalibration approach so that we have an agent that is dynamic rather than static. And also, it is not mutually exclusive with the solution that I will be discussing in a minute. On the contrary, these elements of solution are complementary and should be used together to build a better RL agent. So now let's look at the performance. So we see that it learns something in samples on the training data set, but the average performance on the validation data is much lower than on the training data. So in other words, the strategy that this agent has learned on this non-stationary historical trajectory, it does not generalize well to new unseen data. So this is the fundamental problem of non-stationarity. So we have a training PNL of around 9 and a test PNL of 0.8 with a standard deviation of 4.6, so it varies quite a bit. So now, we mentioned that a full realization is really a one sample data set, and we can't really work with that. But if we generate n realizations, then we can apply reinforcement learning. So how are we going to do this? Well, first, we will create a stochastic model of the assets that we're trading, with a few of its parameters being calibrated on some historical data if needed. And this stochastic model is what I refer to as our hypothesis. And then we will generate n simulated trajectories using our stochastic model. And we train our reinforcement learning agent on those rather than directly on the historical data. And the main claim about this approach is that it prevents overfitting. When you apply it, your reinforcement learning agent will learn what is optimal on average over a representative sample of the possible realizations of your stochastic model of the environment. And this is a direct consequence of the fact that we're essentially running a Monte Carlo simulation of different simulated trajectories and optimizing our RL agent on those. So if you're a bit familiar with Monte Carlo simulation theory, what they do is that they calculate expectations or integrals over trajectories. So without going into any more formality about this, the fact that this method works is a mathematical consequence of the application of Monte Carlo simulation. So in other words, this works because instead of taking an average over time steps, which we showed doesn't work very well, we're taking an average over time series. So because we have a one sample data set, the Bayesian approach tends to be very useful. So in the Bayesian approach, we can build in domain expertise. So for example, decades of literature of asset modeling, things like known stochastic volatility models and all that. We can build in constraints. Let's say that we want trendless, risk-neutral models. We can build in prior beliefs about the random probability distributions and all that. So in my experience, probably because of this, probabilistic programming tends to work particularly well for the stochastic modeling part. Personally, I use PyMC3. There's other perfectly fine probabilistic programming frameworks like Edward Figaro. And I would also mention that in my experience, GANs, generative adversarial networks, don't work very well for this kind of thing because you can't build in domain expertise and constraints easily. So it ends up overfitting on various superfluous aspects of this time series. And the name of the game at this stage is really to discover the most parsimonious model you can think of that mimics the mechanics of the asset we're interested in. Making the least amount of assumptions possible matters more than finding all of the possible patterns of predictability in the data. And this makes it a problem not particularly well suited to high flexibility black box modeling approaches. And another reason is that neural networks are great at modeling structure, but not so great at modeling randomness. Probabilistic programming is much better at this. Okay, so now I will show some code where I do what I just, the solution that I just mentioned. So now we're going to show the use of simulation-based training of our agent. We will use as our hypothesis or our stochastic model, the same model as we use to generate the data. Now this, of course, assumes perfect modeling of the underlying DGP. And this may seem like a bit of a stretch for now, but I'll get back to that point. So in the outer loop, instead of using a single historical trajectory, for each iteration, we will generate a newly simulated trajectories from our stochastic model. And this is what we will train the agent on. But otherwise, everything is as demo 2. And one thing you'll notice is that because we evaluate and train the agent on the same data generative process, it should be obvious that given a sufficiently large number of iterations, we will get the same performance. At least in this case, where our stochastic model matches exactly the underlying data generative process. But notice also we get something for free with this method. We get an estimate not just how well on average we can expect our strategy to perform in the future, but we also get a notion of uncertainty in the form of the standard deviation. And we will use this to validate our hypothesis. So if the performance of our optimal agents on the historical training data, so the data that we use to calibrate this model, is reasonably within range of our confidence region, we can conclude with reasonable confidence that we model the underlying DGP properly. And if the performance of our optimal agent on the historical validation data, so data that was not even used to research or calibrate our stochastic model, if that's reasonably within range of our confidence region, then we can conclude with reasonable confidence that the parameters we assume to be stationary are indeed stationary, at least for the validation period. So here we have the in-sample or training periods PNL. So it learns something, and this generalizes well, of course, on the validation examples or trajectories. So we see that the average PNL across these simulations was 12.42, and we get information about the standard deviation. And in the code, I simulate the fact that we started from some historical trajectory when we calibrated the data, and we have some validation data set we reserve for the purpose of validating this model. And we see that, so the PNL of this optimal strategy on our historical training realization was 13.87, which is well within 12.4 plus or minus 4.7. And similarly, on the validation data set, we also had a result that was fairly close to our expected range. So here, of course, we would conclude that our stochastic model is a good representation of the underlying data, which of course it is. So I ran these 3 experiments, or these 3 demos, 10 times each, and I aggregated the results in this table. When the data is fully stationary, as expected, the performance of the agent is very high, and it generalizes very well from training to test data. For the non-stationary data, when we train on historical data directly, we get a fairly high training set performance, but it fails to generalize well to the test data. And when we train on these simulations, we get a performance that is, in this case, about 2.5 times better than the test performance of the second experiment. And if we can assume that our stochastic model is a good representation of the underlying DGP, then we can expect the generalization performance to be that, plus or minus some confidence interval based on the standard deviation from our simulated performances. So assuming that the stochastic model is a good representation of the underlying DGP is key in that last sentence. And one criticism you might have about this approach is, didn't we just trade overfitting for underfitting, right? And my argument for that, or my response to that, would be that we actually traded a problem that is a consequence of the data with a potential problem that is a consequence of our model. So the data isn't under our control, but the quality of our model is. And moreover, we gain a more complete measure of the expected future performance of our strategy. So again, here in this demo, this was the best case scenario where the stochastic model is exactly identical to the true generating process. And yes, there is a risk of underfitting, and this is why we do our model validation afterwards, to see if we're missing important features in our model. And there's also a risk of assuming parameter stability where there is none, and this is why we test for generalization on a validation data set. And in practice, it turns out that this method works quite well. I've used it successfully, but like training neural networks, practice makes perfect. So I think this is the best way to convince yourself that this is a decent methodology, is to actually go ahead and try it. And I would also mention that you don't really need to perfectly model every aspect of the mechanics of the data generative process. You only need to properly model the aspects that are relevant to our trading strategy, either because our strategy directly uses that information, or because we know that this information will impact our PNL. So for example, if I get in and out of positions at a sufficiently high frequency, then trends might become somewhat irrelevant. Or if I quote passively, then simulating the spread might be overkill. On the other hand, if I'm mean reversion trading, then simulating the stochastic volatility is very likely to be relevant because my entry and exit thresholds are directly related to the current volatility. So the process as a whole is very similar to the scientific method when you think about it. So you start by establishing a hypothesis based on deduction, domain expertise, observation, even intuition to some extent. You model this hypothesis, and then you might need to infer some parameters from the data, and then you optimize your agent on simulations from this DGP. And then you need to test your hypothesis. So does the optimized agent perform similarly on the real data, and does it do so even out of sample? So this brings the question of properly cross-validating this or validating your hypothesis. So you have a generalization test that I refer to as A in this picture. This is when we test how well the performance on the historical in-sample data is predicted by the mean and standard deviation of the simulated performances using your optimal training strategy. If the historical performance is well within the confidence interval predicted by the simulation performance, we can say that the stochastic model correctly represents the true data with respect to the parameters that matter for our strategy. If, on the other hand, the historical performance is well below or very different from the expected range, then with high probability, we are underfitting. So there is some aspect of the mechanics of the data that our stochastic model is not capturing, and we should go back to the drawing board. The generalization test B, which I refer to as the stability test, here what we do is we compare the simulation performance on unseen historical data. So if test A did well, but test B did not do so well, what it suggests is that there are some parameters that we assume to be stationary, but actually are not. So the probability distribution of some parameter in our stochastic model has actually drifted since we calibrated it. And then this is not a test, but a relationship that you might see, which I call C, between the calibration or training set and the validation set, is that sometimes you'll see very different results between the training data and the validation data. Essentially, this is a measure of the historical drift in parameters. So this isn't a test, but it shows how much historically the parameters of the underlying data generative process have drifted, causing a change in historical performance. But as long as those two values are within the expected range by the theoretical, let's say, performance, then there's no problem. It's natural for this drift to occur. So if both the accuracy test, the relationship A, and the stability test, relationship B, give acceptable results to us, then we can consider that our hypothesis is good enough. And this brings up the question of distinction between stable and unstable parameters. So stable parameters in our model of the DGP, the probability distribution of these is the same in the training or calibration data as in the evaluation data. In other words, their values are stationary enough that we can rely on them to generalize to future data points, or at least in a pragmatic sense. Whereas the unstable parameters, these are parameters that are both stochastic and non-stationary, and they need to be modeled as such in order to avoid making false assumptions about them and therefore overfitting. So the strategy will be trained to trade optimally in spite of their randomly drifting nature. So the key element of this approach is that we make no assumptions of non-stationarity, or rather no assumptions of stationarity, I should say. We evaluate the effects first. The Monte Carlo simulation will allow us to successfully optimize the agent in a way that will generalize if and only if the parameters we modeled as stable are indeed stable, and the unstable parameters were modeled as such. So the unstable parameters must be modeled as non-stationary stochastic processes. Now, in contrast, machine learning and reinforcement learning algorithms will not be able to make these distinctions automatically between stable and unstable parameters. They will invariably overfit. So assumptions of stability are built into these algorithms. So in general, you can think of it this way: these stable parameters are the pillars that hold our trading strategy through time. If it weren't for them, it would be all entirely random and there would be nothing to optimize. Okay, so how do we identify this parameter stability? In PyMC3, so in the probabilistic framework that I use, there's the Gaussian random walk. So I model the parameter as a random walk, and I visualize the estimated values. And I ask myself, does it look stable or is it drifting in some way? Can it be better modeled as some stochastic process? And typical examples of, or candidates or elements of solution for this is random walks, Einstein-Uhlenbeck processes, which we've seen in the demo, and Poisson jumps. Now, I don't go into more detail in this presentation with this, but if you're interested in code examples of doing this, you can have a look at my blog post titled The Curse of Non-Stationarity, which I'll give the actual URL in a few slides, or actually in this slide. So references and related work, my blog, and The Curse of Non-Stationarity, which I just referred to. This is where you would have more information about this. And that concludes my presentation.
All right, thank you, Simon. That was great. We are moving on to the Q&A portion now. We've received a few questions so far, so Simon, you can get started.
Okay. Can you give the name of the book reference you mentioned earlier? What other papers on reinforcement learning can you recommend? So I think that this slide on the references at the end kind of summarizes this. I think it answers that question. Okay, what is the significance of PNL? Okay, so that's a good question. I'll answer it in a slightly more general way. That I will also include something that I wanted to discuss, but I didn't have time to discuss. So reinforcement learning agents or methods and their closed custom dynamic programming, they rely on a theorem known as the Bellman equation. So roughly, it states that the value of taking a certain action in a certain state of the environment is expressed as the immediate reward received from taking that action, plus the time discounted sum of future expected rewards, given that you will be making the optimal actions in those future states. So let me show you the code. So let's look at the code that calculates these rewards. First, well, let me go with the outer loop. So when I train the agent, I first, for each iteration of the simulation, I call current reward to calculate the immediate reward. So the immediate reward is this here. So it is the PNL change from time t to t plus 1 on the spread, depending on whether we're currently long, short, or flat on the spread. Okay, so it's simply from time t to t plus 1, and to answer more directly the question, so the total PNL at the end of a simulation is the cumulative sum of these immediate rewards. Okay, so I save this into the state action rewards memory, and when comes the time to train the RL agent here at the end of one simulation, I calculate the expected future rewards using a trick known as temporal difference learning. So if we look at the code, so instead of calculating the time discounted sum of all the expected future optimal actions rewards, as would be required by the Bellman equation, instead I add the estimated value of the next state's optimal action based on our current model of the state value function. So to do this, I feed the next state to get max q, which given that state, so let me go to that function, get max q. So given that state, which is the state at time t plus 1, it finds what is the best value we can hope for by comparing all the possible actions. Okay, and it basically gets the max. So q is the q value, so the expected value of taking that action in that state. And I should mention also something else that I'm doing here, which is a bit of a hack, to be honest. Instead of taking the immediate reward at time step, the next time step, I'm actually taking a time discounted average of the next 100 data points for my actual reward. And I'm doing this strictly for empirical reasons. I noticed that doing that helped me learn, helped the learning process for this particular problem. So anyway, so I add these things together here, right? The immediate reward plus that expected future reward. And that becomes my training label. Now, so that's the question for the actual training label, the reward of it. But the cumulative, so the P&L for a simulation is really just the sum of all those individual time steps from the spread times the current position. So times 1 if we're long the spread, times -1 if we're short the spread, and times 0 if we're flat. So if we're flat, of course, the P&L at that point in time is 0. How do you get to a good stochastic model in the first place? Well, that's a very difficult question, and I guess very long question to answer. I'm hoping that the blog post that I wrote, The Curse of Non-Stationarity, might give you a more concrete answer to that question with some code examples. So hopefully that will answer that question. Can we try to use the bandit algorithms in finance, like considering the multi-armed bandits? So the problem with the multi-armed bandits approach or technique is that it assumes that there's only one state. It's kind of a stateless thing, right? So reinforcement learning is really like one step of complexity beyond the multi-armed bandits by adding the notion that there's an environment where the state changes and it reacts differently to different states, whereas the multi-armed bandits only has multiple actions that it can take, and it just needs to learn the optimal one on average. So I find it hard for me to see how this simpler version of the problem applies to finance, because in finance you always have external variables. You have a current state, like my current position on the spread in our example. So I think that's why I go for reinforcement learning rather than the simpler bandit algorithms. With AlphaGo, does that game have stationary variables? So that's interesting, because so games like chess, Go, pretty much any game that exists is very different from, let's say, the game of finance, right? So the rules in Go are the same forever. All the constraints in the game are the same forever. They don't change. So there's nothing to adapt to in a larger sense. So once it has learned something that is optimal, then you're good to go. So everything in the AlphaGo problem, let's say, or the problem of solving the game of Go is stationary. Is it designed for a single asset or multiple assets? It can work for both. It's just that multiple assets means that your stochastic model might be somewhat more complex. Do policy gradients not take into account the non-stationarity of the data? No, they do not. That's a simple answer. Maybe hidden Markov models can be used to detect parameter instability. That could help detect the different random distributions. I have not looked into that, so maybe that's true, maybe, I don't know, to be honest. Are we able to run all your demos locally based on your code on GitHub, or would we need any external data or price source? It is entirely self-contained, so you can easily check it out from GitHub and run it locally, as long as you have XGBoost installed, and NumPy. And I think I use Python 2.7, so you need to have that version available. But yes, you can easily run that code. Any particular discount factor you use? I use 0.95 for not for theoretical reasons. I just played with I just tweaked that value, and I found that this worked fairly well. Yes, that's a good question. Other than using the P&L as a measure of performance, are there any statistical measures which allow for significance analysis? Well, to be honest, personally, I don't use the P&L directly as a measure of performance, although I do in this demo, because this is more of a toy example. It's a conceptual example or a proof of concept. But in any real trading context, I will use something more like a Sharpe ratio or a Sortino ratio. And there are ways to do that cumulatively. So yeah. So that my fitness function would usually be something like that. Okay, so could you explain again what makes the data set in demo 1 stationary and the data set in demo 2 non-stationary? So that's a very important question, so I'll go over that. So stationary DGP versus time varying DGP. In my stationary DGP, so the mu, so again, to recap, mu is the long-term equilibrium, or the mean to which my mean reverting process tends to revert in the long run. So in the stationary version, this mu is 100, it's constant, and it never changes. So I'll have a process that is stationary around the level of 100. On the other hand, on my time varying BGP, I start at 100, but at each time step in my data generation loop, I have this going on. So every 200 steps, I allow the mu, the long-term mean, to actually change a little bit by an increment from a Cauchy distribution. And also once every, is it 2000 time steps? So anyways, every once in a while, let's say, I allow it to jump radically by somewhere between -3 and 3. So by doing that, now my mu is something that from time t0 to time n will have a very different value. It will evolve over time. This is the non-stationary core of that data generative process. Under which situation will the reinforcement learning be best to apply as opposed to other machine learning methods? So I don't know if the question is about contrasting reinforcement learning versus, let's say, supervised learning or things like that, or if it's this versus dynamic programming, but I'll assume that it's the first. So the reinforcement learning is about, you have a specific problem. It's an optimization problem. So there's something that you need to do in an environment and you're trying to do it optimally. Whereas the other machine learning techniques typically are more of a predictive nature, right? So I'm going to, let's say, try to predict something, and in one of the references that I have, so this one here by Michael Kerns is actually a good example. He makes the case that, so in his opinion, what he says is that in finance, you're better off using reinforcement learning because it's very difficult to separate the problem of prediction from all of the cost of making the trades. So you might very well have a predictive model that is able to forecast some price, let's say, but it is still not profitable because you don't include in that model all the market frictions that are involved in actually executing the trade. So Michael Kerns argues that it's very difficult to separate the execution parts of trading from the pure theoretical prediction part. So for that reason, he prefers to frame most problems in trading in terms of reinforcement learning. And I would tend to agree with that. Yeah, so I guess that's my answer. Does your model's performance depend on the number of data points heavily? So the version that I presented in the second demo, where I trained directly on historical data, yes, it depends quite a bit on the number of data points. Whereas in the approach that I'm proposing in this presentation, what we're really doing is that we're creating our own model. So we're not depending directly on historical data. So from there, once you have your stochastic model, you can generate an infinity of data points for training purposes. So essentially, it becomes more a matter of computational resources than a matter of how much data I have available. That's a good one. So which parameters in your data generative process would you usually fit with real historical data? Well, I guess it depends a lot on the type of strategy that you're doing. In my case, I do a lot of mean reversion trading and pairs trading, as you might have guessed from my presentation. So what I do is very dependent on stochastic volatility. So I definitely spend a lot of time calibrating the scaling parameters of my random variable. So in other words, let's say the standard deviation of parameters of my stochastic model on data. And in contrast, I do not fit trends to the historical data. I always build risk neutral models because I have this, I guess, assumption, let's say, that trends in finance are very unreliable, so I never include them in my models. I just always assume a zero trend. Okay, so yeah, that's it for me.
All right, so we are out of time for questions now. If you have a question that we didn't get to, you can send it to us at events@quantopian.com, or you can post it in the Quantopian forums. I'll make sure Simon sees it. I want to thank Simon for a great presentation. We had some great questions, and thank you all for attending. Have a great day.